Mid-February 1943, Sidi Bouzid, Tunisia. The captured M4A1 Sherman tank rolled to a halt in the desert sand, its American star still faintly visible beneath the freshly painted German cross. Officers from Heavy Panzer Battalion 501 gathered around the vehicle, notebooks ready. This single, fully operational American tank, taken during the Battle of Sidi Bouzid, would soon trigger a crisis of confidence among German engineers, one that would influence their tank development for the rest of the war. The lessons ahead wouldn't come from thicker armor or stronger firepower, but from something the Germans had never prioritized: reliable automotive engineering that simply didn't fail. Painted on the hull were the words, War Daddy 2. Its serial number read, USA 3067641, built by Lima Locomotive Works, and it belonged to Company G of the 1st Armored Regiment, 1st Armored Division. German reconnaissance troops had driven the Sherman over 350 kilometers across the rugged North African desert to the port of Sfax, a 4.5-day journey. With every kilometer, they discovered something that challenged their assumptions about American industrial capability. The engine never overheated. The transmission never failed. The final drives kept working flawlessly. German tank crews, used to constant breakdowns even on short movements, watched with growing unease as this enemy machine rolled on effortlessly through terrain that would have crippled their own vehicles. At Sfax, War Daddy 2 was loaded onto a cargo ship bound for Germany under strict orders from the Army Weapons Office. The tank had to arrive intact and fully operational. German intelligence had seen reports about American tank production before, but now, seeing the machine itself brought those numbers to life. The Sherman embodied mass production on a level Germany could never achieve, built with engineering principles they had never mastered. As the ship crossed the Mediterranean, Wehrmacht engineers prepared for a series of tests that would expose uncomfortable truths about their own limitations and about America's strengths. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy 2 rolled off the rail car, bearing the designation Versuchsfahrzeug 259 and German license plate WH058941. Engineers had already marked every surface with stenciled notations, showing armor thickness and angles. Kummersdorf, located about 25 kilometers south of Berlin, was the primary testing site for both German and captured Allied vehicles. Here, teams of meticulous engineers would measure, test, and analyze everything, from track tension to transmission efficiency, documenting every result in exhaustive reports. The Sherman was about to undergo the most comprehensive mechanical inspection German engineering could design. Specialists from multiple branches examined it closely. They photographed every component, measured every clearance, and studied construction methods that seemed shockingly simple compared to their own. The transmission immediately caught the attention of the powertrain experts. While German tanks used straight-cut gears that demanded extreme precision and constant maintenance, the Sherman's transmission used herringbone-cut gears, a design that spread stress evenly across multiple teeth. This approach, standard in American manufacturing since the 1930s, provided durability with minimal precision requirements. German engineers had dismissed such gears as too complex to mass produce. The Americans, however, had been making them by the thousands. The tests began with standard automotive trials meant to push every system to its limit. Engineers drove War Daddy 2 through obstacle courses simulating battlefield terrain, monitoring fuel use, engine temperature, and transmission performance. After each run, they tore down parts to inspect wear, lubrication, and stress. The results shattered long-held German beliefs about the trade-offs between power and reliability. The Sherman performed well in all areas, and excelled in one the Germans had never mastered: long-term endurance without maintenance. Further testing revealed key differences in engineering philosophy. The Sherman's 5-speed transmission, with synchronization in gears 2 through 5, allowed smooth shifting without double clutching. It made the tank almost as easy to drive as a civilian car, meaning soldiers with basic training could operate it effectively. German tanks, on the other hand, required highly trained drivers who had to master complex clutching techniques just to avoid damaging their transmissions. The Continental R975 radial engine in this Sherman proved equally impressive. It maintained consistent power in temperatures that would have caused German engines to overheat or lose output. The cooling and air filtration systems, though simple, worked flawlessly, even under dusty desert conditions that had crippled German machines. Every feature reflected a design mindset focused on practicality over perfection. June 6–7, 1943, Hillersleben Artillery Range. Reich Minister Albert Speer arrived to oversee a major armaments conference attended by industry leaders and senior Wehrmacht officers. The event featured head-to-head climbing trials between German and captured Allied tanks. There, standing beside the newest Panther aus D and a massive Ferdinand tank destroyer, was War Daddy II, the American-built machine that had quietly rewritten everything the Germans thought they knew about tank design. Albert Speer, Germany's armaments minister and Hitler's direct appointee for weapons production, needed to see firsthand what American industry was capable of and how German tanks compared to those of their enemies. The demonstration was meant to provide clarity, but what Speer witnessed that day offered answers few in German engineering wanted to accept. The Sherman began its climb up the test slope smoothly. Its 5-speed manual transmission, synchronized from 2nd through 5th gear, shifted without hesitation. The engine maintained steady power all the way up. The driver handled it with ease, showing the intuitive control that would become the Sherman's hallmark. Then came the German machines. The Panther, powered by a 700-horsepower Maybach HL-230 engine, managed to keep pace but just barely, and only with significant effort from its crew. The massive Ferdinand tank destroyer, weighing 65 tons and featuring an advanced electric transmission system, stalled halfway up the hill. Recovery crews scrambled to restart it as senior officers and industry leaders watched in silence. The scene was embarrassing. In his later memoirs, Speer would recall the Shermans he saw during an inspection tour in Italy in October 1944. Reports of their cross-country mobility had impressed him deeply. Shermans could climb mountains German tank experts had once deemed impassable. Speer noted that the tank's powerful engine, relative to its weight, gave it better off-road performance and agility than German designs. The 26th Panzer Division had confirmed this advantage in combat reports. Coming from the man in charge of Germany's armaments program, these observations carried enormous influence. A few weeks after the trials, on June 27, 1943, Das Reich newspaper published an article describing the Sherman as one of the notable achievements of North American laboratories, calling it a praiseworthy product of the North American steel industry. The piece highlighted its serial production methods and the almost arrogant standards of the American automobile industry that made such manufacturing possible. It even praised the tank's gyro-stabilized gun, the first of its kind, acknowledging American innovation. Officially, these comments were framed as propaganda, but privately, the tone inside German engineering offices was one of alarm. American tanks weren't just adequate, they were better engineered for long-term battlefield use. At Kummersdorf, testing continued throughout the summer and fall of 1943. Engineers pushed the Sherman to its limits, recording operational ranges over 2,000 kilometers before any major maintenance was required, about 4 times farther than early model Panthers could go in real conditions. Transmission efficiency surpassed that of every German tank tested, with far less power loss through the drivetrain. The synchronized gearbox allowed easy, reliable shifting, no double clutching or delicate rev matching required. Then came the final drives, another painful revelation. Panthers used a flawed design inherited from the Tiger, relying on straight-cut gears housed in undersized casings that couldn't handle the tank's 45-ton weight. Failures were common, and many Panthers in North Africa and on the Eastern Front had to be abandoned after traveling less than 100 kilometers. The Sherman's final drives, built with the same herringbone gear design as its transmission, were almost indestructible. Even after decades in storage, post-war restoration projects found many original Sherman components still fully functional, a testament to their robust design and generous safety margins. By late 1943, Kummersdorf's data had been compiled into detailed internal reports distributed across the Wehrmacht's technical branches. The findings were sobering. They revealed that American automotive engineering had reached a level of maturity Germany lacked, despite its scientific talent and precision craftsmanship. Mass production techniques allowed the Americans to use looser tolerances, what German engineers would have called sloppy, yet their vehicles were far more reliable in real-world conditions. Interchangeable parts meant field repairs could be performed quickly with basic tools. German tanks, by contrast, required factory-level precision and specialized equipment just to stay running. The deeper analysis revealed an even more fundamental truth. America's industrial and cultural familiarity with automobiles shaped its tank design philosophy. Before the war, the U.S. had a thriving car culture. Millions of citizens owned and maintained vehicles. Germany, however, had little civilian automotive experience. Cars were luxury items for the wealthy or political elite. The much-hyped Volkswagen project, launched in 1934, had produced fewer than 1,000 cars by 1939. This difference carried straight into military design. American tanks were built for mechanics with ordinary automotive backgrounds. German tanks required specialized training and expert supervision. By late 1943 and early 1944, field reports confirmed what engineers already knew. German tanks, like the Panther, were mechanically fragile. Crews were instructed to avoid frequent gear changes, as the transmissions were prone to braking, especially third gear, which manuals warned against using except when absolutely necessary. Drivers were even told not to turn while reversing, since doing so could destroy the gearbox entirely. In the end, the Germans realized that while their tanks looked superior on paper, the Americans had mastered something far more valuable: engineering for endurance, efficiency, and the realities of war. Pivot turns in the Panther were only possible when both tracks had equal traction, limiting its maneuverability in uneven terrain. Even small rocks or debris caught in the running gear could jam the drive sprocket, forcing hours of maintenance. These flaws existed despite the Panther being built in specialized factories by skilled workers using Germany's best materials. The Sherman, on the other hand, came from a completely different design philosophy. It was created by automotive engineers from General Motors, Ford, and Chrysler, men who understood mass production and efficiency. They used proven commercial components and existing supply chains wherever possible. Its transmission was produced by multiple companies, including Caterpillar, Buick, and Ford, all to identical specifications. Every part was interchangeable, meaning a transmission from one manufacturer could fit perfectly into a tank built by another. This level of standardization was routine in American industry, but virtually unheard of in German tank production, where each factory's small design variations made parts incompatible. Through 1943 and 1944, more captured Shermans arrived at Kummersdorf, including tanks taken from British forces in Italy and Soviet units on the Eastern Front. Each underwent the same extensive testing, building a detailed database of American tank designs across multiple production runs. The British modified Firefly variant drew special attention. It mounted a powerful 17-pounder anti-tank gun. German engineers were impressed that the Sherman's turret ring was large enough to accept the bigger gun with minimal rework. That adaptability revealed something the Panther completely lacked: room for future growth. The Panther, rushed into service to counter the Soviet T-34, had no space or structural margin to handle major upgrades without a full redesign. Reliability trials soon followed. Engineers drove the Shermans across hundreds of kilometers of rough ground, logging every repair and failure. They compared these results to field reports from Panther and Tiger units fighting on the Eastern and Italian fronts. The contrast was shocking. Panther operational readiness averaged below 40% for most of 1943, with some units reporting catastrophic lows of just 20 to 25%. Many battalions had periods where fewer than 1 in 5 tanks were combat ready. By comparison, Shermans consistently maintained much higher operational availability across all theaters. German records detailed the Panther's troubles with brutal honesty. During Operation Citadel at Kursk in July 1943, only 16% of Panthers were fit for combat. Most were sidelined by mechanical breakdowns rather than enemy fire. By December that year, readiness had risen to just 37%. February 1944 held steady at 37%. April reached 50%. And by May 1944, it finally hit 78%. While the numbers improved as design flaws were fixed, even the best Panthers never matched the Sherman's reliability straight off the production line. Engine lifespan data told the same story. The Sherman's diesel variant could run over 3,000 kilometers with proper maintenance. The Panther's engine rarely lasted 1,000 kilometers, even after extensive improvements. In March 1944, German engineers proudly reported the latest Panther engines could now last 700 to 1,000 kilometers, barely one-third the endurance of a standard Sherman. The Sherman's synchronized transmission required little upkeep and was forgiving of driver mistakes. The Panther's gearbox, by contrast, demanded constant care. Third gear broke so often that crews were told to skip from second to fourth gear entirely. The Panther's final drives often failed within 100 to 200 kilometers, while the Sherman's herringbone gear final drives remained reliable even after prolonged combat use. Field reports from German units that used captured Shermans confirmed Kummersdorf's findings. As their own armored forces deteriorated, German commanders eagerly pressed any captured American tanks into service. Unlike the Soviet T-34s, which required modifications before use, Shermans needed no alterations. They simply worked as intended. German crews who had suffered repeated breakdowns in their own machines were astonished by the Sherman's reliability. Letters and reports described how these tanks allowed them to focus on tactics instead of worrying about mechanical failure. Panzer regiments noted that Sherman operators could maneuver and fight with confidence, while Panther and Tiger crews often struggled just to reach the battlefield. A striking example came in January 1945 during Operation Nordwind. The 10th SS Panzer Division captured 12 M4A3 Shermans from the U.S. 43rd Tank Battalion at Hatton and Hillsheim. Formed into the division's 13th Company, these tanks saw combat for the rest of the war. Used as reconnaissance and reserve vehicles, they performed reliably with minimal maintenance, exactly as German testing had predicted years earlier. In the end, German commanders recognized what Kummersdorf had already proven. Reliability determined real battlefield strength. A Sherman that reached the fight with its gun ready was far more valuable than a Panther, no matter how powerful, broken down 20 kilometers behind the front. By January 1944, as the Wehrmacht retreated on multiple fronts and more captured equipment arrived at Kummersdorf, one truth had become undeniable. American engineering had mastered the art of building machines that didn't just perform, they endured. Engineers carefully examined the M4A1 equipped with the Continental R975 radial engine, documenting its performance and comparing it with other Sherman models. They also tested the M4A2, powered by twin General Motors 6046 diesel engines, noting its excellent fuel efficiency and unique operating characteristics. The M4A3, featuring the Ford GAA V8 gasoline engine, was considered by American crews to be the best of the series. Despite their differences, every variant shared one essential trait: exceptional reliability, thanks to solid engineering and consistent manufacturing quality. German engineers, used to wide variations between their own tank manufacturers, were impressed by the uniform quality across all Sherman models. The diesel-powered M4A2 particularly caught their attention when examined at Kummersdorf. The Soviets had received 4,102 of these tanks through Lend-Lease, and many ended up in German hands during the Eastern Front retreats. The twin GM6046 diesel engine offered performance equal to any Sherman variant, while consuming much less fuel, a major advantage as German fuel supplies dwindled. Germany had tried developing diesel engines for tanks but gave up due to manufacturing challenges and the complexity of fuel injection systems. In contrast, the U.S. produced diesel and gasoline Shermans side by side without interrupting output, proving a level of industrial flexibility and technical skill Germany could never match during wartime. By March 1944, reports from General Heinz Guderian, Inspector General of Panzer Troops, noted that Panther tank reliability had finally reached what he called acceptable standards. Engine life improved to about 701,000 kilometers, and final drive problems were mostly resolved through design and manufacturing upgrades. But this achievement only brought the Panther up to the level of reliability the Sherman had already reached back in 1942. The German Army celebrated progress that merely caught up to standards the Americans had mastered from the start. The comparison grew even more painful as German production suffered under worsening resource shortages and Allied bombing. In April 1944, a massive Royal Air Force raid involving 322 aircraft devastated the Maybach engine plant at Friedrichshafen, the worst single blow to German tank production during the war. The nearby ZF gearbox factory was also destroyed, halting tank engine and transmission output for 6 months. When production resumed in November, quality had sharply declined. Slave laborers, often forced to work under brutal conditions, resorted to sabotage, jamming cigarette filters in oil lines, misplacing gaskets, and assembling components incorrectly. Sherman factories, meanwhile, operated safely in the U.S., staffed by motivated workers earning fair wages under good conditions. The key difference between American and German tank production wasn't knowledge. Both had brilliant engineers, but industrial capacity and design philosophy. German engineers focused on maximizing performance, not practicality. Their tanks looked impressive on paper, but their complexity led to poor reliability in real combat. The Panther's powerful 75mm KWK-42 gun and heavy armor overloaded its drivetrain, making it prone to breakdowns. The Tiger's strength came with extreme maintenance demands and the need for highly trained crews. These flaws might have been manageable if Germany could produce enough tanks and parts, but by 1944 it couldn't. Allied bombing, fuel shortages, and raw material scarcity crippled production. In contrast, American engineers, drawing from decades of automotive mass production experience, built tanks that could be made in the tens of thousands and maintained by mechanics with basic training. The Sherman's powertrain used proven components adapted from trucks and cars. Its electrical system even included a backup generator to rotate the turret when the main engine was off. A small detail German designers dismissed as unnecessary luxury, but one that proved invaluable in battle. By spring 1944, German units across all fronts were reporting worsening mechanical failures. Panthers often had to be transported by rail for trips over 100 kilometers because their final drives couldn't handle long marches. Orders were issued limiting tank movement to prevent breakdowns before combat. Even the Panther recovery vehicle, built to tow disabled Panthers, suffered from the same reliability problems. In many units, mechanical issues destroyed more tanks than enemy fire, with up to 70% of losses caused by breakdowns. Meanwhile, U.S. production reached record levels. 49,124 Shermans rolled out during the war, more than all German tanks combined. Thousands were sent to British forces, over 4,000 diesel models to the Soviets and many to Chinese units in Burma, where they proved devastating against Japanese armor that was far behind both American and German designs. Every battlefield where Shermans fought confirmed what the tests at Kummersdorf had already proven. Properly maintained Shermans kept running under conditions that would cripple or destroy German tanks. German crews who captured and operated Shermans consistently praised their mechanical reliability in letters, reports, and post-war interviews. Reports from the Eastern Front mentioned that even the complex Chrysler A57 multi-bank engine, with its 5 connected engine blocks, was easier for German mechanics to service than their own tanks, which required specialized tools and constant fine-tuning. The Ford GAA V8, admired by Allied crews for its reliability and strong power output, seemed remarkably dependable to German mechanics used to Maybach engines that constantly demanded adjustment of valves, ignition timing, and carburetors. The General Motors twin diesel engine, rejected by the U.S. Army as slightly less reliable than gasoline types and sent mainly through Lend-Lease, still outperformed any diesel tank engine Germany had ever produced. The Sherman's design also offered a hidden strength, built-in engineering margins. The same transmission and final drive components originally intended for the 30-ton M4, with 400 horsepower, required no major redesign to handle the 42-ton M4A3E2 Jumbo assault tank, which carried much heavier armor. These components even managed 650 horsepower in experimental engines without failure or reinforcement. German engineers viewed such overbuilding as wasteful, unnecessary strength that used scarce materials and raised costs. American engineers saw it as smart insurance, room for upgrades, battlefield durability, and long-term value. By summer 1944, as the Allies invaded Normandy, German tank commanders knew their disadvantages ran deeper than armor or gun caliber. American artillery dominance, devastating air support, and unmatched logistics overwhelmed them regardless of technical specifications. But it was the Sherman's reliability that gave American armored units their greatest edge. U.S. tank battalions could attack, fight, pursue, and immediately prepare for the next mission without long maintenance breaks. German panzer divisions had to conserve their few working tanks, knowing that every mile driven wore out fragile components and brought another breakdown closer. The difference in operational readiness determined which side could maintain the offensive and which had to ration its strength. Even German use of captured Shermans proved their superiority. During the Battle of the Bulge in December 1944, the 150th Panzer Brigade tried to obtain American vehicles for a secret infiltration mission. German planners specifically wanted Shermans because of their reputation for reliability. They received only 2, and just one was in good enough condition to run. That single Sherman never reached combat because of traffic jams that stalled the entire operation. For a mission requiring dependable vehicles deep behind enemy lines, only American-built equipment could be trusted to keep running. On January 23, 1945, Germany officially admitted defeat in automotive reliability. A Panzer Commission report documented catastrophic final drive failures across all tank types: 500 in Panzer V's, 370 in Panthers, 100 in Tigers, and around 200 in Hetzer tank destroyers. General Wolfgang Thomalla, Chief of Staff under General Heinz Guderian, summarized the impact plainly. Under such conditions, organized tank operations were impossible. Troops lost faith in their vehicles, often abandoning them because they feared being stranded. German tanks that looked terrifying on paper couldn't perform the most basic duty of a combat vehicle: reaching the battlefield and completing their mission. As Soviet forces closed in on Berlin in early 1945, the Kummersdorf testing center prepared for evacuation. Engineers rushed to pack research data and ship it west, hoping to save valuable findings for post-war study. Some captured tanks, including at least 2 Shermans, were pressed into emergency combat service alongside German models defending the approaches to Berlin. Those Shermans kept fighting until they were destroyed by enemy fire or left behind when fuel ran out. The German tanks beside them, including Panthers and the few remaining Tigers, broke down from mechanical failures at shocking rates, even to crews already accustomed to such problems. The story of War Daddy II and the dozens of other Shermans tested at Kummersdorf reveals one of the clearest industrial contrasts of World War II. German engineers, trapped in a system obsessed with theoretical perfection, created tanks that dazzled on paper but failed in sustained combat. American engineers, guided by decades of automotive manufacturing experience, built machines that were less elegant but far more dependable. In war, the weapon that works when needed always defeats the one that might be superior, if it can make it to the fight. Post-war studies by American and British analysts confirmed exactly what the German tests at Kummersdorf had already shown. Systematic studies of destroyed German tanks revealed that mechanical failures were just as common as combat damage as causes of loss. Final drives shattered under stress, transmissions seized from poor lubrication or driver mistakes, and engines burned out from overheating or oil starvation. Germany's obsession with individual vehicle superiority and impressive specifications blinded its engineers to the importance of reliability and ease of maintenance. They built tanks that no conscript mechanic could service without specialized training. Machines powered by engines demanding constant attention from experts, supported by a logistics system overwhelmed by the need to supply countless unique parts to widely scattered units. The lessons learned from testing at Kummersdorf deeply influenced post-war German tank design. When West Germany began developing the Leopard 1 main battle tank in the 1950s, engineers deliberately prioritized reliability and maintainability over raw performance. They studied American automotive engineering principles and applied them to military design. The Leopard 1 reflected much of what had made the Sherman successful: a strong, durable powertrain with generous design margins, components that were easy to service with minimal tools, standardized parts for quick field repairs, and growth potential for upgrades without full redesigns. The result became one of the most successful tank designs of the Cold War, serving in numerous armies for decades. The captured Shermans at Kummersdorf, including War Daddy II, its name still painted on the hull, represented more than just enemy hardware. They were physical proof that mature industrial capability and sound, experience-based engineering mattered far more than theoretical innovation disconnected from production reality. German designers had pursued ever more advanced specifications, believing superior technology could offset their shortages in materials and numbers. They were wrong. American engineers built reliable vehicles because they understood that logistics, maintenance, and operational availability not raw technical performance, determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between the Sherman and German tanks shaped not only battlefield outcomes but also broader lessons about industrial capacity and its decisive role in modern war. Germany entered World War II with technological advantages in many areas, backed by brilliant scientists and skilled engineers. But it lacked the industrial depth to sustain those advantages under the pressure of full-scale war on multiple fronts. The United States, by contrast, began the war with weapons that were less sophisticated in design but had an unmatched industrial base, capable of producing them in overwhelming numbers, while continually improving quality and reliability based on field feedback. This industrial approach, embodied by the Sherman, proved far more effective than Germany's pursuit of perfection through complex, fragile designs. The U.S. built nearly as many Shermans as Germany produced tanks of all types combined, while also supplying allies, producing vast amounts of other weaponry, and maintaining the highest living standards of any major power during the war. Germany could not match this output even before Allied bombing crippled its production. The math was simple. A Sherman with a 75mm gun that reliably reached the front was far more valuable than a Panther with superior firepower that broke down before battle or required days of maintenance after every mission. A battalion with 80% of its tanks operational could fight and win, where one with 40% could barely function. Reliability wasn't a luxury. It was the foundation of combat effectiveness. German tanks consistently failed this test. American tanks consistently passed it. By mid-1943, Kummersdorf's tests had already proven it beyond doubt. Even as German commanders kept deploying Panthers and Tigers that looked formidable on paper, they faced the same problem: machines that couldn't be trusted to run when needed most. The Sherman didn't win the war through superior armor or firepower. It won through industrial superiority, expressed as reliability, consistency, and maintainability. German engineers at Kummersdorf saw the truth clearly in their data by 1943. They documented it in reports and confirmed it through rigorous testing. But understanding the problem and fixing it were two very different things. Germany's war economy lacked the ability to redesign its production system around reliability, while fighting for survival on multiple fronts. American industry, built on decades of automotive experience, had already mastered reliability in civilian vehicles and effortlessly extended those principles to wartime production. War Daddy II, the single Sherman captured in Tunisia and tested for months at Kummersdorf, told the whole story through its flawless performance. Every kilometer it ran without failure showed that German tank design had taken the wrong path, valuing impressive specifications over practical reliability. Every test that proved American engineering excellence was proof that industrial maturity and hands-on manufacturing experience mattered more than theoretical design perfection. In the end, War Daddy II was an ordinary tank among tens of thousands, but what it represented was extraordinary and devastating to German confidence. It was proof that Germany had already lost the industrial war long before it lost the military one, and that no amount of technical brilliance could overcome the overwhelming power of reliable, scalable, and practical American production.